it started to record.
Okay, so thank you for the invitation. It's a great pleasure. My talk is split into two pieces. And the first half will be very general, where I take some results from the groups I don't really know that well. Plus, the second half is a bit more technical. Some groups I do know very well. Okay. So,
Excuse me, may I interrupt you? So the sound is really low. When Laurent was speaking, it's loud enough, but the speaker is very difficult to hear.
Where's the mic?
Can you do something with the mic?
This comes from where the microphone is, and I guess the microphone, in fact, is in front of me. So what I can do is I can turn the computer, and then the microphone will be correctly oriented.
is this better?
It's better
Yes,
for the...
it's better, thank you.
On the other hand, I cannot then direct. So you will always see all four boards.
Is this better?
The sound is better.
Okay.
But now I cannot control the boards. So you will always see all four boards. I cannot zoom on any of the subboards.
Oh, I see.
But the blackboard, it's easy to see, so maybe it's good this way.
Perfect.
Okay.
Thank you.
And you have an extra 1 minute and 30 seconds to compensate for this.
Okay, actually, it's correct now. All right, so we're talking about dynamical systems. So in this case, X is a compact metric space. Okay, and G is a group or a semi-group that acts continuously on X. Okay, so for every element in my group, I have a transformation from X into itself. It's a continuous map, it's a homeomorphism, depending on whether G is a semi-group or a group. A lot of what I say today applies to groups that are more general, but for our results, we're taking the group to be the integers, right? So the integers will act on my space. Okay, and so that means that my action is invertible, and I want to define the LS semigroup. So this is E of XT. So this is the compactification of the action. Okay, so it's the compactification of the group, okay, in this case Z, in the topology of pointwise convergence. Okay, so this is a very natural thing in dynamics to look at, because my space is compact, if I take a sequence of points, there are always subsequences which converge. So it's a natural object to study. Okay. So F, which is a function from X to X, is in the LS semigroup, if and only if F of X is the limit along some net or alpha filter G alpha say of X for each X in X. So this is what it means to be the topology of pointwise convergence. Okay. Okay, so you can ask, is the LS semigroup a group? Does it consist of homeomorphisms? So what are the known results? So here's one. I'm going to call this an example, but with a theorem. Oh, actually, before I say this, I will say one more thing. Okay, so the LS semigroup is quite important, characterizes proximality. So what does proximality mean? So if I take two distinct points in my space, X not equal to Y, these are proximal if there is some sequence, and now I'm just talking about Z actions, but this generally, just to make the notation simpler. Okay, so there's a sequence of integers such that the distance t to the nk of X, t to the nk of Y tends to 0. Okay, as X tends to 0. Okay, and a space is, a dynamical system is distal. So XP is distal. If it has no proximal pairs. Okay. Okay, so what do I mean when I say that the LS semigroup kind of captures proximality? Is the following. So X and Y are proximal. If and only if there exists an element in that LS semigroup such that it collapses these 2 points. Okay, so already you see that in general, elements of the LS semigroup are not going to be injected. All right, so examples of semigroup descriptions. So you can say, well, what if I have a distal system? So no proximal pairs, okay? So if X, E, G is distal, okay? Therefore, the LS semigroup is actually a group. The elements are not necessarily continuous, but the elements are invertible. Okay. And it's equicontinuous. So what I will just define this to be is that it's basically a group rotation on an abelian group. Then I have that E of XP is a group of homeomorphisms. Okay, so let me call H a group. H is an abelian group. This therefore the LS semigroup is a group of homeomorphisms. So equicontinuous rotations are definitely contained in the set of dynamo in the collection of distal systems, but the opposite is not true. So the other extreme, and these are the shifts that we're going to look at today. So generally speaking, the spaces that we look at are totally disconnected. Okay, so A is a finite alphabet, Z is the integer. Finite alphabet. And obviously, okay. And what's a topology? The topology is the product discrete topology. Okay, so two infinite sequences are close if and only if they agree on a certain window around the zero index. Okay, so topology. So A has a discrete topology. Okay, and X has product topology, or A to the Z has a product topology. So X has to be closed. So I can talk about the, yeah, so X must be closed. So that's my space. And sigma is the shift map. Okay, so sigma of the point xn. We just put n here is equal to xn plus 1. Okay, so I just shift to the left. Okay, this is the shift map. Okay, and x sigma is called the shift. So the results that I'm going to talk about today are about shifts. Shifts are pretty generic in dynamics. And so another extreme example of an LS semigroup description is if I take X to be the full binary shift. Okay. Then the LS semigroup is sigma here. That is going to be Stone-Check compactification of the natural unit. So this is the other extreme, or of Z, yeah. Thank you, because it's two-sided. Okay. Okay, so on the one hand, you have some very nice Ellis groups. And then on the other hand, you have a rather ugly object, depending on how you look at it. Sorry. Okay, so the question is, what about other systems? Okay. And so I think I read this in an article by Glasner. He said the problem with computing these LS semigroups is, generally speaking, these limits are not filters. They're filters, okay? They're nets. They're not sequential. And so this comes from work of Angela Kohler from 1995. Okay, and she kind of identified a dichotomy for these LS semigroups. So she kind of injected Borgan-Fremlin-Pallegron dichotomy, which I know very little about. And I think she was just working with Z actions. Okay, but she said either the LS semigroup has cardinality at most 2 to the LS naught, or the LS semigroup has cardinality at, well, equal to 2 to the 2 to the LS naught. Okay, so this is the dichotomy. Okay, and for these LS semigroups, you can talk about elements of the semigroup in terms of sequential convergence, whereas here you can't. So she calls these systems regular, all right, but we call them tame. Okay, so a system is tame if the LS semigroup of the system has cardinality of most 2 to the L. Okay. So if you're interested in describing LS semigroups, you want to be able to describe these tame semigroups. Okay, so the question is, which systems are tame?
That's the same as being retransable?
Pardon me?
Is it the same as being retransable?
I don't think so.
Okay.
Yeah, don't think so.
I'm sure you
So no. Okay, so that's the question. And Huang gave some part of an answer.
Maybe an stupid question. Is
Yeah.
it true that there is actual borrow like a standard borrow space in some actual way?
For the LSM group, when it's,
If it's smaller than the our.
I don't know the answer to that. That's a really good question. I would say no, but I could be wrong. Yeah, I think it's not clear to me. Okay, so the answer to the question, what systems are tame, is not closed. Okay, so Huang in 2006 showed that if you have a abelian group action, right, and tame, then XPG is what's called almost automorphic. So I'm going to define that in a minute. Okay. So what does it mean to be almost automorphic? Okay. So for that, I have to define. Okay, so this example I gave, or I said that if you have a group rotation, then it's basically a rigid isometry. This is an example of what's called an equicontinuous factor. Okay, so every dynamical system. So I'm now going to define what is almost automorphic. Okay, so every dynamical system XT has a maximal equicontinuous factor. Okay, so this is maximal equicontinuous. What is a maximal equicontinuous factor? So it is, you can think of it of many ways. The abstract definition is I have a maximal group. Maybe I call it H. So this is the dynamics. This is plus alpha. This is an abelian group. Okay, such that this diagram commutes. Okay, so it's the maximal equicontinuous structure that you can find inside your dynamical system.
So this is for abelian group action.
Yeah, I can do this for what I've drawn here is for Z actions, but for abelian group actions, this would be an abelian group acting on this space. Okay, so this is for Z action.
Yeah.
TZ. Another way to think about it. So this map, so H plus alpha is generated by the continuous eigenvalues of your dynamical system. So these are lambda, such that, so lambda usually in your circle, such that there exists a continuous function, it's continuous here, with f composed t equals lambda. So if you look at all of these eigenvalues, you can generate a group in the circle, and this is going to be the Pontryagin dual. So there are ways to, many ways to describe this, but you can think of it as the maximal rigid action in your space. And these are the pictures that we look at. So here is H. Okay. You can think of your dynamical system as a kind of fibered product over H. So here is X. Okay, so this could be a point Z in H. X lives as some kind of product, but for it to be almost automorphic means that there has to be a fiber which is injected. Okay, so XP is almost automorphic. So AA, if there exists a Z in my maximal equicontinuous factor such that the cardinality of its pre-image is 1. Okay, so that's what almost automorphic is. Okay? So as you see, this is a really strong condition, right?
So you assume minimality of X, or?
Yeah, I'm always assuming, yes, thank you. Thank you, X is minimal. So I haven't said what minimal is. So what is a minimal dynamical system? It's a dynamical system where the orbit of every point is dense in your space. And I assume that throughout. Okay, and so Glasner generalized this to amenable groups, all right? So generalize, same result, generalize one result to amenable groups. And minimal, always minimal. Okay, so Huang's result is not an if and only if, right? Huang's result is very much, if it's tame, then it's almost automorphic. There are lots of systems that we know that are almost automorphic, and I will describe in a minute a few. But the converse is far from true. Okay, so you can have almost automorphic systems which are actually not tame. And in fact, I would say most of them are not tame. Okay. So how did Huang prove his result? He proved his result by finding an uncountable family of points, such that if you take two distinct points in this family, they're going to be proximal in a strong sense. Okay, but that's not what, there's another description of how you can show that something is tame, and this is due to Karen Lee. condition for non-tameness. It's the following, and I'm just saying for shifts. For shift dynamics. So X in A to the Z is non-tame if you can find two disjoint sets, B0 and B1. In the alphabet, such that for any function which takes values 0, 1, okay, there exists a point in my space X such that X sub give me a sec. Yeah, and there exists a sequence, right? There exists a sequence such that for any choice function on the integers, I can find a point X and K, a point X such that I can put in the index NK the value P of K. Okay, so this is like a full shift structure occurring in your dynamic system.
X and K belongs to V underscore.
Yeah.
Yeah.
Okay. Thank you. Just give me a sec. Is in V sub C of J. Thanks.
The interesting direction is the other one.
Yeah, so it's if I can do this, then I can conclude that it's not tame. Okay. It's a two-directional thing, but that's the way we're going to use. Okay, so I said to you that most tame systems, that tame systems are almost automorphic, that if you're almost automorphic, doesn't mean that you're tame. Okay, so here are some results. So theorem number 1 is due to Gabriel Foreman, Eli Glasner, Tobias Jager, which I'm sure I'm pronouncing wrong, and someone Herzl, okay, which says the following. So now we just look at almost automorphic systems, and we ask when are they almost tames? Okay. So if you have an abelian group, you can have there's a Haar measure on it. So from what I say now, mu is a Haar measure. So if Xt is tame, then the measure of the set of all Z in my maximal equicontinuous factor, which has a preimage greater than 1, this is 0. So I can see this quite a lot, but in fact, the measure of these points Z, which carry these large fibers, is 0. So this was in 2018, I believe. There's another theorem.
So this is for V actions?
Yeah, for Z action. Wait, I mean, maybe I think it's even true for G actions, but I think I'm talking about Z actions right now. Yeah.
I think we need to measure, so it must be a mean.
Yeah, so I said Z actions, so this is just a group.
I mean, you don't try to measure those practice issue. So,
Yeah.
we-
No, I'm on Z actions, so I always have that the maximal equicontinuous factor is going to be a B. Okay, so there's another result, I think also roughly around the same time, also Gabriel Foreman and Dominic Kwetniak, okay, which says that if Xt is almost automorphic, And now they're specifying the maximal likely continuous factor over an irrational rotation. Okay, so I have T alpha. Let's say it's R mod Z. So into R mod Z. So X goes into X plus alpha mod 1. Okay. Yeah.
Let's add something. So it's about the question about the measure.
He's Johannes.
Yeah, this system always happen. This continuous factor always have a measure because it's like going to continuous section to always have a invariant measure. So it's
The harm measure for that.
yeah. So it's you don't need an ability.
Yeah, the statement definitely makes sense, but
Okay, but I'm only talking about that action.
Yeah, but I remember in the back of my head that they have other conditions that are the same as in the paper line.
What is the condition?
That G has an invariant measure on X.
Yeah, but G has an invariant measure on X, but this is a measure on the equicontinuous factor.
Then it's almost automorphic, and I can get it. But it's
So mu is the harm measure on the maximal equicontinuous factor. Okay. So, Foreman and Kwetniak asked this question. They asked, okay, what if I have a shift? This is quite, if you know these examples, there are examples here called Sturmian shift, okay, which are almost automorphic over an irrational rotation. Then the set of Z such that the pre-image of Z is greater than 1 is a Cantor set. So these are two different conditions. This talks about the regularity of the measure. Okay. So sorry, the mass of what we call the irregular fibers. Okay, so the fibers which have more than one pre-image. If it's almost automorphic over an irrational rotation.
And statements?
Yeah, thank you. And non-tame.
Yeah, this also.
Yeah.
So it's not yet.
Non-tame, then the set of singular fibers is a Cantor. So these results are different. Yeah.
so now I recall this first there. Indeed, for this to make a little sense that the system is almost automorphic. Now.
Well,
Say tame, and then you need then it should be almost automorphic. But for this, you need the condition that X has a invariant measure on X.
okay. Okay. So these two theorems tell you that you need to study the set of singular fibers, and you need a way to describe it. And Gabriel Foreman, who is the F here, gave a talk that interested me and Johannes and myself. So what I'm about to talk about is joint work with Gabriel, Johannes, who is that guy, and myself. Okay, so Gabriel gave a talk about these results and the systems that Johannes and I this sort of study. They're almost
Sorry, so
yeah.
can I just ask about this theorem too?
Yeah.
So this Z, they live in the circle, yeah?
Yeah, they live in the circle because that's the maximum continuous
So the
factor.
set where pi inverse of Z is bigger than 1 is invariant under the action, yeah?
Yes.
But there's no invariant Cantor set under the action. So.
Okay, let me see if there's another thing that. In fact, this is an if and only if. So I don't know.
You see what I'm saying?
Yeah, so if you're saying that if I have an irregular fiber and I shift it by the action, it's also irregular. And you're saying that there are no such.
Yeah. So are you sure this is not upstairs?
I'm wondering if it's up there. Yeah. Thank you. Yeah, so X,
So it's
such that,
pi inverse of 5x, yes.
X is, thank you. X is in here. Such that the cardinality, that's a nice improvement, is a Cantor set.
I mean, I'm not sure this is true, I'm just trying to make.
No, it is true. If and only if. So this is true. Then XT is non-tame. If and only if.
So is it for every kind of this singular point you have, it says that for every singular point the fiber.
No.
For all the single.
So all the set, so the set of all points which live in a singular fiber, if you put them all together, then it's going to be a Cantor. Okay, so so this is specific to when the maximal equicontinuous factor is a rotation. Okay. And the question we were interested in is what happens if the maximal equicontinuous factor is what's called an odometer. Okay, so I'm going to say H plus 1, where H is the inverse limit, okay, of Z mod Sn of Z, where Sn divides Sn. Okay. So those are the systems that that we were interested in.
The set of these fibers,
Yeah, the singular fiber.
it is not closed. So
Well, why do I need to close?
because it's a Cantor set.
Okay, so maybe I have mauled this theorem. Clearly, I have mauled it in two different ways. So maybe we could discuss it afterwards, okay? It does depend on X because the factor map depends on X.
As it is written in the real.
As it is written,
As it is written, it is real.
yeah, I don't know why it's here as written. But I'm happy to hear you explain why it's weird.
The exit in the fiber, such that the fiber is greater than 1.
I think what is meant in the set of X is to be the pi inverse of 5x is not single. I think this is the.
Well, pi inverse of Z is a set, right? Okay, it's weird because I have to also qualify that Z is any point.
Because the union over all Z.
Yeah,
Like this
that's right.
three,
Z is any point whose pre-image has more than one point. I take the union over all such things. And then I get, I hope, a Cantor set.
Okay.
Okay. And now I'm starting to run out of time. So I would like to, I will state our theorem. But before that, I'm going to make a definition. I'll say that XT is circuit if it is endless automorphic over such an odometer. If its maximal equicontinuous factor is this odometer, so maybe I'll just write inverse limit Z mod and head. So these are specifically the things which have an odometer as a factor and which are almost all of them. So our theorem, and I will define it, and I'll spend the rest of the time defining what thick means. Okay? So every thick Toeplitz shift is non-tame. Okay. And so the corollary of this is that a Toeplitz shift of finite rank, so I will also define this, is non-tame if and only if it has uncountably many singular fibers. Okay, so let me see if I can get the quantification right here. The set of all Z, well, I will just say this. If it has uncountably many singular fibers. Then here I'm counting over Z. Okay? So the Z such that this has a cardinality greater than 1 is uncountable. Okay. So once again, it's not about measures, it's not about theorem 2, but whatever it is, but it's about the size of the singular fibers. And before I define what thick is, I would like to give some idea for how we came about the proof, keeping in mind the Karen-Lee condition. Okay, so what I'd like to talk about are automatic sequences. So these will give examples of Toeplitz. So how do I generate an automatic sequence? Okay, so a sequence that lives in an alphabet is automatic. So I'm going to say L automatic if there exists a finite state machine. Okay, so this is actually a deterministic finite state automaton. So what does this mean? There's a set of states. There is a map, theta, from the set of states cross 0 up to L minus 1 into the set of states. So this you can think of as giving you the instructions for edges between states. So I'll draw a picture in a minute. There's an initial state, so this is an initial state. There is an output alphabet, and there is an output map. So tau goes from the set of states into the output alphabet, such that, and I'll draw a picture in a minute, okay, such that use of n is going to be the label of the state, so I have to put a tau. I apply theta, the transition map, starting at my initial state. But what path do I follow? I follow the path which is given by the base L expansion of n. Okay. So n sub L is the base L expansion of. Okay, so let's give an example. So here is such an example. And I'm going to actually just look at examples where this is trivial, but everything I say can be extended to the situation where I have an output. And here is an example of such a thing. They're much easier to draw than they are to define. So in this case, so the set of states, I have 3 states here. Okay. This arrow tells me that this is my initial state. Okay. L here is going to be 2. I have edges labeled 0, 1, and 2. Because I have no output map, that part is trivial. But if I had an output map, I would just have to give these states an image under tau. Okay. And so, for example, I don't know, what if I wanted to know what U7 was? Okay, the entry generated by this machine. I first need to take the number 7. I need to look at its base 3 expansion, which is 2, 1, right? And then I need to read this, starting at the initial state and following it in direct reading. Okay, so what I get is I get 2 followed by 1. So here, U sub 7 is going to be B. Okay, so that's what is an automatic sequence. Okay. So now I suddenly talked about automatic sequences, but I really wanted to talk about dynamical systems. So given an automatic sequence, how do I define an automatic system, a dynamical system, which is called an automatic shift? So given a sequence, I can now define a language. So given an L automatic sequence, U sub n, okay, I define a language, which is the set of all words that are seen. Okay, this is so I define a language. Given a language, I can define a shift. So here, A is going to be my output alphabet, which is also my state set. Is in my language for all K less than or equal to M, K and M. Okay. So this is a shift dynamical system, which is automatic. And a theorem of decking. So we call this X theta, I'm going to call an automatic shift. Okay. And the theorem of Kamai and decking from 1977, okay, is that the maximal equicontinuous factor of these dynamical systems is an odometer, okay? So the maximal equicontinuous factor of X theta sigma, okay, up to a finite factor. So there's something called the height, okay, but basically it's the L-adic odometer crossed with possibly a finite Z mod H then. Okay.
So can I ask something?
Yeah.
So this odometer, did it come from the least significant?
No, but from the most significant. That's why I put this arrow, but it doesn't matter because if you want to read it in the least significant way, there's an automaton that will also generate the same sequence, just not the same automaton. But for substitutions, it's natural to look in the sense of direct reading. Okay. So now I'm talking about these systems, but we have to talk about almost automorphic systems, right? So this is another result of decking, which is that X theta is almost automorphic, if and only if. Okay, so maybe I need to take a power But if I look at this automaton, it has to be synchronizing. Okay, so what this means is that, and I'm only going to define it for pure automatic sequences, but the definition is quite easy if I have outputs. Okay, what this means is that there is one state which accepts the same, all instances of edges which have this fixed digit. Okay, so in this example, A is a synchronizing state because all edges labeled 0 come into A. Okay, so that's what it means to be synchronized. Okay, so this is almost automorphic if and only if it is synchronized. If and only if the machine is synchronized. Okay. Okay, so I have 1 minute and I'm going to borrow another minute. So what does this have to do with our results with Gabriel? So now we know when these automatic sequences generate almost automorphic systems. And there's another result in earlier work that I had, which says the following, okay? So let me write it this way. There is a graph, G theta, okay, which completely describes the singular fibers of your maximal equicontinuous factor, okay, which is obtained, so it's constructed, okay, which is obtained from the machine, from what I call M theta, okay, and such that the set of all z such that maximal, such that pi inverse of z is greater than 1, so the set of all singular fibers, okay, are the labels of infinite path in G theta. Okay. So how do I do this? And then I will stop. If I have this machine and I'm going to create this the graph G theta for this machine, so there is a graph G theta whose vertices are labeled by subsets of cardinality of A, of my alphabet, of cardinality strictly greater than 1. Okay. So how do I get such a graph? I start with ABC, which is definitely a subset of this alphabet. And I follow these edges. So the edge 0 will always take me to A. Okay? Because all of the edges for A, B, and C end in A. What about the edges 1? Well, the edges 1 map the alphabet into itself. Okay. What about the edges 2? The edges 2 match the alphabet into B and C. And now I repeat this game on B and C. And if I repeat the game on B and C, I will actually see this, I believe. So I'm almost at my graph. But I have to erase everything which has cardinality 1. Okay, so G theta, and I have to reverse arrows. So G theta, and I'm going to change it a little, looks like this. And I said I have to reverse these arrows.
You did it, you reversed twice.
I did a reverse, okay. It actually doesn't matter in this case, okay. And now this is about for automatic sequences. But now our result with Gabriel is actually about Toeplitz shift. So what changes? What changes is we don't have one graph, we have a sequence of graphs. Okay. So thick means, remember I said it's thick If it's thick, it's non-tame, okay? Thick means I have a sequence G theta M such that I have a double path. So for automatic sequences, the sequence is stationary. It's always the same graph with a double path. So I take this picture and I draw a sequence of these graphs. And this is my double path. Okay, this goes to 2, and this goes to 1. This is my double path, and it goes down forever. Okay, because I have a sequence, in this case, a stationary sequence of graphs. And that is what gives me the possibility of making the Karen V result actually work to show that it's not there. Okay. So I will stop there because I'm already 4 minutes over. Thank you.
Questions or comments or remarks from the audience? Definitely, I had a comment that so you are proving that the set of singular fibers is it's an automatic, it's a regular, it's an omega regular set.
So regular in automata theory
Yes,
means that the language is acceptable. Yes, that's right.
but for infinite sequences.
Yeah, but also for automatic sequences, yes, the answer is yes. But for general Toeplitz, because I have a sequence of graphs, I don't know how to turn that into a regular.
So the general statement is that
The general statement.
an automatic, the things you get from automatic sequences, so L automatic shifts are building blocks for Toeplitz shifts.
Correct. Exactly. So the way you want to think about it is.
And what is the relation to constant length substitutions of length L?
So automatic sequences without output are exactly substitution sequences of length. So if you, like I said, if you ignore this, then this is another way to define the constant length, a fixed point of a constant length substitution.
And then automatic is more general.
And then automatic.
And then Toeplitz is even more general.
And then Toeplitz is more general. Instead of one finite state machine, you have a sequence of finite state machines. And you have to take an inverse limit when you generate sequences.
Ah, oh, yes.
Yeah, and that's why you're going to have, instead of one graph, you're going to have a sequence of graphs.
Yes, so then there's no chance of obtaining anything like regular language, because you have an infinite number of input possibilities already built in from the definition.
So how can you read the odometer from the automaton? I mean, how do you get what is the odometer?
Well, the odometer, so the maximum continuous factor here is Z3, 3 added integers. How do you read
This
it?
is what you said there. Okay.
Yeah, you read it by looking at the labels of the edges.
Okay. So this is just this. Well, there's this times Z over NZ.
HZ, yeah. So this
It's
is
an H.
so this is the height. So this is a finite factor that sometimes appears, and then you cannot see it directly.
But then, depending on the values of H, this may not be minimal. H is equal to L, for example.
No. H always is cofine to L.
Ah.
Yeah, H is always cofine to L.
Are there some generalization to a situation where it's not C action, for example, C
Yes. Yeah.
or amenable group like
Yeah, there is. So there's a lot of work by Samuel Petit and Maria Isabel Cortez who study these Toeplitz actions. Okay, so they're not Z actions. They don't look at sequences indexed by Z. Okay, they will look at sequences indexed by groups. And then they define what it means to be Toeplitz.
I mean, that does, like, your work makes sense in this, like, it translates to this, setting or.
I have never thought about it, but I think it does. Yeah, because you have group action, right? And if they're, especially if they're abelian or amenable, you can talk about these notions of being almost automorphic. They also have maximal equity factors.
Yes, but you cannot talk about automata, right? The automata is very specific to Z because somehow.
Well, you can use automata to generate in sequences indexed by Z to the D or N to the D, right? Z to the D. You basically, instead of inputting the base L expansion of N, you input the base L expansion of a pair of numbers. You can use such a.
It's more tricky for a circle than if there's some.
Yeah, it's like automatic sequences just, maybe I'm just saying something stupid, it's just a subshift of finite time.
No.
No.
Automatic sequences are definitely not subscripts of finite type. In fact,
They're meaning.
they are.
They're meaning.
So
Well,
the finite type has periodic points
So
for the loop.
yeah, another way to think of automatic sequences is they generate shifts. So subshifts of finite type have positive entropy. These automatic shifts, they have zero entropy. And furthermore, if the primitive substitution, I'm not going to define what that is. Basically, there's finitely many points which are proximal. Okay, there's finitely many points which are asymptotic, which are left asymptotic. Okay, so so the way to think about this is there are finitely many points with more than one path. So that there.
I think it's a good time for at least 5-minute break. Should we give you an extra? Maybe let's make it a 10-minute break, unless, well, are there some questions from our Zoom participants? Doesn't seem like it. Okay, so